Hello everyone, you're watching the Space Channel. Darkness, penetrating radiation, infinite gravity, emptiness, and an incredible crampedness together with an infinite size. All of this is terrifying, and what is even more frightening and astonishing is that everything just listed surrounds us. In our universe, there are countless places with such horrifying conditions. Each of you would probably not want to spend even a moment there. But every one of you would like to take a look at these monsters. But is everything really that scary? Today, we will look at a series of the most terrifying astronomical objects, understand what makes the universe so dark and at the same time, blindingly bright. Try to figure out what infinity looks like and compress stars to the size of a tennis ball. So let us sort this out together. White dwarfs and neutron stars. Stars are born, live, and die. They are mostly born in the same way, from a cloud of gas and dust. When they die, they also leave behind gas and dust. But the very process of death for each star can happen differently. Depending on its mass, at the final stage of its evolution, a star can turn into a white dwarf, a neutron star, or even a black hole. All three of these types of objects are characterized by very high densities, whose description is carried out by particle physics and quantum mechanics, and their gravity by the general theory of relativity as well. So you can imagine how dense their matter is. 1 teaspoon of neutron star matter weighs approximately 1 billion tons. How about that? The sizes of these objects are comparable to the sizes of planets, but the conditions there are so extreme that the problems of the equations of state and the internal structure of neutron stars have still not been solved. At the same time, the structure of white dwarfs has been studied to some extent based on Chandrasekhar's theory. It is hard to imagine what is happening inside neutron stars. In essence, hydrostatic equilibrium in neutron stars is maintained on the one hand by gravitational pressure, and on the other hand by the pressure of degenerate fermions, that is, neutrons and electrons, with very high energy values. A typical temperature in the surface layers of neutron stars reaches about 1 million degrees. The internal structure is similar to that of the Earth. There is something like a surface with more or less reasonable densities, then a crust, and then an inner neutron fluid that consists of admixtures of protons, electrons, and muons. The density in the center rises to about 10 to the 15th grams per cubic centimeter. At the same time, neutron stars also possess strong magnetic fields that produce many interesting observable phenomena. A neutron star with a powerful magnetic field is called a pulsar, and pulsars are potent sources of electromagnetic radiation that are often detected as periodic pulses. We will discuss white dwarfs, brown dwarfs, black dwarfs, neutron stars, magnetars, and other similar objects in a separate video. Black holes. If you take a small stone and throw it upward, it will fall back to the Earth after a few seconds. Could you, here on Earth, throw it in such a way that it would leave the Earth forever? For this, you would need to give the stone the second cosmic velocity, which for the Earth is 7.9 kilometers per second. You are hardly able to do that with a small stone. The speed of light in a vacuum is the ultimate speed in the universe, and nothing can move faster than that. This is a postulate. There exist objects for which the second cosmic velocity is comparable to, or even greater than, the speed of light in a vacuum. Then, not even light would be able to escape from the surface of such an object, and it would be absolutely black. The natural philosopher and priest John Michell came to this conclusion back in the distant year 1784. This is how the idea of the existence of black holes, compact astronomical objects, was born. But only after the creation of the general theory of relativity did scientists become seriously interested in them. And only in the 1970s was the source of X-ray radiation in the constellation Cygnus, which had been discovered 5 years earlier, officially accepted as a black hole. Since then, a great deal has already been learned about black holes. Black holes represent the ultimate degree of compactness to which stellar evolution can develop. To create a black hole from, for example, the Sun, you would need to compress it to a size of 3 kilometers, and for the Earth to turn into a black hole, you would need to compress it to a radius of 0.88 centimeters. Having already called a neutron star a frightening and strange object, we cannot help but call black holes strange as well. It turns out that black holes are actually not black. We talked about this in previous videos. There is a phenomenon called Hawking radiation. Its explanation is straightforward, but not entirely correct. You may have heard about a particle and an antiparticle that are born and annihilate near the event horizon, and then one of them falls into the black hole while the other is emitted. But this is a thought experiment to clarify the Hawking process. The radiation process itself is more complex, so we have made a separate video to explain it. As a result of radiation, black holes evaporate and eventually disappear. All of this is described by the thermodynamics of black holes. For example, supermassive black holes completely evaporate only after about 10 to the power of 100 years. By then, the universe will have cooled completely. But the most incomprehensible thing in a black hole is the singularity. A gravitational singularity is a point in space-time at which the curvature of space becomes infinite. In the case of rotating black holes, and in the general case, they really are rotating. The singularity has the shape of a ring of 0 thickness. Can you picture that? Some people believe that a wormhole may be contained in the singularity, and that someone who ends up in a black hole could move to another place in the universe. But so far, quantum mechanics does not confirm such a hypothesis. In any case, once you cross the horizon of such a monster, you will be spaghettified. That is, the non-uniform gravitational field will stretch you out like a strand of spaghetti, and you will simply fall onto the singularity. At the dawn of radio astronomy, astronomers began to discover strange objects that stunned them with their anomalous properties. The sources of radiation from these objects were not visible in optical light, and they shone very brightly only in the radio range and at many different frequencies. Their emission spectrum was unlike anything else, which made it impossible to understand their nature. At the same time, the object was located at a tremendous distance from us, because there was a very large redshift. The first assumptions about what these objects might be were quite varied, ranging from white holes to the edge of a wormhole. But as it later turned out, the source of this unusual radiation is matter from an accretion disk falling onto a supermassive black hole. Thus, a quasar is located in the center of a galaxy and emits more energy than the entire galaxy in which it is located. Because of this, the radiation from the stars or matter of the galaxy itself is not even observed. The emission spectrum of quasars is broad, spanning the X-ray to the infrared. In addition, quasars are also active sources of gamma rays. A quasar is accessible for observation even to an amateur astronomer. With a telescope that has an aperture, that is, the diameter of the primary mirror or lens, of about 300 millimeters, it is already possible to see quasars that have a stellar magnitude of about +14. In the optical range, they appear rather faint from Earth due to their enormous distance. But still, why are they so bright? The energy of the radiation is produced in the accretion disk of the black hole through the rotation and the enormous friction of the material. A supermassive black hole can convert from 5 to 32% of the mass of the material into energy, which is tens of times more than the process of nuclear fusion in the depths of stars like our Sun. Intergalactic voids. The stars around us, including our Sun, are part of the galaxy called the Milky Way. We know that our galaxy is not the only one, and that billions of galaxies form clusters. These large concentrations of galaxies form even larger-scale structures, galactic filaments, or threads. But through these threads, which are woven like a web, enormous empty regions are observed. Where did the voids in the universe come from? The universe has a sponge-like structure. Voids occupy most of the space in the universe. The diameter of such empty regions can reach hundreds of millions of light-years. One way to observe an individual void is to study it with optical and, more often, radio telescopes in search of something within it. Superclusters and voids are usually studied, identified, and discussed together because they are believed to have a common origin. The formation of voids is closely connected to the evolution of the entire universe. Some astronomers believe that the voids formed during the inflationary period, when the universe's temperature was incredibly high and quantum fluctuations were proliferating. They led to the formation of regions with an inhomogeneous matter density. The voids, in turn, became regions with abnormally low matter density. The composition of matter in the voids is unfortunately unknown. It is tough to detect it through direct observations. But scientists believe the voids are composed of rather massive elementary particles that interact weakly with one another. The idea that the voids may contain dark matter is not ruled out, because light passing by these objects is bent as if through a gravitational lens. Judging by this, there is quite a lot of matter there, so the voids are not so empty after all. The Boötes Void. Scientists believe that the share of such voids makes up about 50% of all the space in the universe. The most considerable void known to us in the universe is the Boötes Void, which was discovered in the year 1981 by Robert Kirshner during a study of the distribution of galaxies in the universe. The void is located about 700 million light-years away from us in the constellation Boötes, in whose honor the void is named. The diameter of this monster is astonishing, about 330 million light-years. A rocket traveling at the speed of light would have to fly for 330 million years in absolute darkness to pass all the way through it. Immediately after this void was discovered, astronomers began to search for at least something inside it. Astronomers were able to detect about 60 galaxies in this enormous empty region. The shape of the void slightly resembles that of a sphere, but it cannot be a black hole because galaxies and intergalactic gas are still present there, though in a minimal amount. One hypothesis about the formation of giant voids is that, around smaller voids, galaxy filaments could merge, intertwining and forming large filaments and walls with empty interiors. In this way, voids merge. Some scientists believe that this is how the Boötes Void may have formed. The discovery of voids, quasars, black holes, and neutron stars has strongly influenced traditional astrophysical and cosmological thinking. And since then, astrophysicists and cosmologists have repeatedly revised their understanding of galaxy formation and the universe as a whole. Who knows? Perhaps in a few centuries we will discover something in space that will overturn even our modern understanding of the universe. That is all for now. If you enjoyed the video, leave a like and subscribe to the channel. See you next time.